We left off with this, male, female vital capacities will vary a little bit, obviously because of size, lung difference, okay? But gas exchange, well, this is a little different. And this is where we actually start talking about how much is being exchanged as it moves around throughout the system. Okay, not only from atmospheric gas coming in, but as it moves through the systemic circuit, it changes. And it changes by quantity. How much? Now, I've already said the most important gas is CO2. We don't really care about oxygen, but we definitely care about CO2. So let's move through this. Gas exchange occurs between blood and alveolar air across the respiratory membrane. It depends on partial pressures of gas. Partial pressures. That means if we have part, collectively they're the sum. The sum is always going to equal 100% or 760. And what is 760? It is millimeters of mercury, but it is 1 atmosphere. Okay? So, it depends on partial pressure and diffuse of molecules between gas and liquid. What is the liquid? Blood. Yeah, blood's a liquid. Okay? So, gas laws. Ooh, now we're really getting into the laws because we have a quiz on Friday. So diffusion occurs in response to concentration gradients. Rate of diffusion depends on physical principles or gas laws. An example is Boyle's law. Okay, we're going to talk about these different laws. So Dalton's law and partial pressures. Okay, composition of air, nitrogen, oxygen, water, and carbon dioxide. Notice the percentages. 78, 20, 0.5, and 0.04. 20% is oxygen. Okay? Composition of air. Now they're talking about this air. They're not talking about this air. They're talking about this air, which is going to change. Okay? So we will not focus on nitrogen, but we will focus on oxygen, water, and carbon dioxide. Look how small the percentage of carbon dioxide is. Yeah, it's pretty darn tiny. And so the thing about this tiny percentage is that's what we actually have our values off of how you breathe. We actually sample the blood and say, wow, we're off. We've got too much CO2 or we've got too much hydrogen. We need to make a change. Okay, Dalton's law and partial pressures, atmospheric pressure, 760, produced by air molecules bumping into each other. Each gas contributes to a total pressure, okay, in proportion to its number of molecules, Dalton's law. Partial pressure. Partial pressure, the pressure contributed by each gas in the atmosphere. All partial pressures together add up to 760, or 100%. Okay? Now, you have to think about it this way. If we go back the other direction, are we getting rid of one and picking up one? Yeah. So their partial pressures are still going to fill in that gap. Now, diffusion between a liquid and a gas. This is Henry's law. When gas under pressure comes in contact with the liquid, gas dissolves in liquid until equilibrium is reached. Soda pop. Don't we have a gas in soda pop? Yeah, we do. Okay, at a given temperature, the amount of gas in solution is proportional to the partial pressure of that gas. The actual amount of a gas in solution at a given partial pressure and temperature depends on the solubility of that gas into that particular liquid. Well, the liquid's always going to stay the same. Because it's not like, Mohammed's like, you know what, today I want to run off of Dr. Pepper. I'm tired of this whole blood thing, it's overrated. I'm going to drain the blood and I'm going to put Dr. Pepper in there. Yeah. Okay? Do you like Dr. Pepper? No? What? You don't like the doctor? I don't know, there's something wrong with that. Okay, well, we'll leave it alone for right now. Okay, so there you go. Increasing the pressure drives gas molecules into solution until equilibrium is established. All right, when the gas pressure decreases, dissolved gas molecules leave the solution until a new equilibrium is reached. And what's the example that they're giving you? A soda pop. Okay, soda is put into the can under pressure, and the gas carbon dioxide is in solution at equilibrium. Example, opening the can of soda relieves the pressure and the bubbles form as the dissolved gas leaves the solution. We call it carbonation, but it's a gas in a liquid. And I used that as an example yesterday. Okay? And it has a law. Henry. Good old Henry likes soda. Isn't it funny they have Henry's soda, too? Memory tool. Just saying. Okay. So, solubility in body fluids. CO2 is very soluble. Very. Okay. O2 is less soluble, and N has very low solubility. Well, we're not going to focus on N. We're going to focus on CO2 and O2. Okay. Normal partial pressure in pulmonary vein plasma, pulmonary vein, that's oxygenated, isn't it? It's coming back from the lungs to the, the heart's an easy answer. Come on. The left atrium. Thank you very much. Trying to get away with the heart, like the heart. Of course, everything revolves around the heart, right? Even the love of food revolves around the heart. Yeah. So, let's see here. The P just means partial pressure, for those who need to know. Okay? And so, partial pressure, CO2, 40. Partial pressure, O2, 100. These are millimeters of mercury. Now, I'm using the numbers generally, but watch what happens as we start to move through the body, okay? Partial pressure of nitrogen, 573. Now again, we're not going to focus on nitrogen, so let's just stick with the 40 and the 100. This is at the pulmonary veins. Okay? So diffusion and respiratory function, direction and rate of diffusion of gases across the respiratory membrane determine different partial pressures and solubilities. Well, if we're going to the tissue, we're going to have higher oxygen and less CO2. Once we go through the tissues, we will have lower oxygen and more CO2. Now, the amount of CO2 is still very, very limited. So, 5 reasons for efficiency of gas exchange. Substantial differences in partial pressures. That's right off the bat. Okay? Distances involved in gas exchange are short. O2 and CO2 are both lipid soluble. Total surface area is large. Okay, and blood flow and airflow are coordinated. Ooh, that's interesting. So in other words, if you have a large amount of CO2 in the blood, we're going to make sure that when you get to the lungs, you have a way to get rid of it. Does everybody get that? If you have a large amount of CO2 in the blood, when you get to the lungs, we're going to make sure you have a way to get rid of it. You have to. You can't just hold on to it, and we already know that because what happens when you hold your breath? Yeah, you pass out or you give up. That's all about CO2. So, partial pressures in alveolar air and alveolar capillaries. Blood arriving in the pulmonary arteries has low PO2, high PCO2. This is arteries. That means we've gone through the heart, we've gone through the right atrium, through the right ventricle, through the pulmonary trunk, and we've entered the lungs. Okay, the concentration gradient causes O2 to enter the blood and CO2 to leave. And we are going to ensure in the lungs that we are dilated and ready to get rid of that CO2. Because if you're constricted like this, can you get rid of CO2? No. No. We're going to dilate and make sure we can get rid of it. Rapid exchange allows blood and alveolar air to reach equilibrium, which means we're going to balance them back out again. Remember, 760 or 100%. We have to equal those numbers again. Now, it doesn't matter if we're on one side or the other, but we have to equal those numbers. A partial pressure in the systemic circuit, oxygenated blood mixes with deoxygenated blood from conducting passageways. lowers the PO2 of blood entering the systemic circuit, drops to about 95. Okay, now these numbers are going to vary because in some cases they talk about just right here in your lungs it's 140. And then we drop to 104. And then we drop to 100. And then we drop to 40 at the tissue. And that's a standard number. Here they're using 100 and then 95. So the numbers are relative. Okay, you're going to see different numbers out there. And I think I put an image up for you guys, didn't I? I'm pretty sure I did. Okay, it has the lungs and it has a little thing to fill in your pressures as they go around. Okay, so partial pressure in the systemic circuit, interstitial fluid, PO2, 40. So that number's good to go. All right, that number's good to go. And then PCO2 is 45. Well, let's back up. 40 and 100. So what did PCO2 go up to? 45. What did PO2 go down to? 40. So what they're talking about is literally at the tissue, we're going to pick up 5 millimeters of pressure from CO2 and we're going to drop off 60. Actually about 55 according to their numbers, but yeah, it's 60. Okay? So do we need oxygen at the tissues? Yeah, we do. And we know internal respiration, cellular respiration produces what? It's not a trick question. What does cellular respiration produce? Water and CO2. Cellular respiration. Cellular respiration, water and CO2. Well, CO2 is a byproduct, right? Aren't we using O2 and we produce CO2 in the process? Okay, so we're picking up 5 millimeters of mercury of CO2 and we're dropping off about 55, 60 millimeters of mercury of oxygen. So let's go back to the basics of this. If we have 100 at the heart, okay, and we drop off a little, they're saying 5, and then from 95 to the tissues, we drop off to meet 40. So it's about 55 right there. That's how much oxygen we've dropped off. Now remember, they're using millimeters of mercury, not percentages in this point, but we are dropping off oxygen. In return, what are we picking up? Yeah, CO2. Concentration gradient in the peripheral capillaries is opposite of the lungs. CO2 diffuses into the blood. O2 diffuses out of the blood. Okay, so at the lungs, we are picking up oxygen and dropping off CO2. At the tissue, we're dropping off oxygen and picking up. There you go. Now they're using these numbers to put it into perspective. How much pressure is being generated at these drop-offs? Or the lack thereof pressure, right? Because don't we go from 100 to 40? Yeah, we do. Okay? So there you go. And this image is actually on your guys' images. If it's not, it'll be on there tonight. Okay? So you should fill in the numbers for where you're picking up and dropping off. And I'll put both of them. I'll put one that's labeled and one that's unlabeled with numbers. Okay? Remember, the numbers are relative. Like I said, other books are going to put you at about 104, and then you lose about 4, so you're at 100, so you drop off 60. This book is saying you're dropping off about 55. And that's one of the images, but there's another one too. So I'll go ahead and I'll make sure you guys have it, but yeah, that's one of the images she has right there. So let me grab that just to show you. This image right here, this is already available to you. So you can easily write in on this one your numbers. Where are you dropping it off and where are you picking it up? Thank you. Okay, so let's back up a little bit. Let's go up here. It's at the lungs. They're giving you an exchange. Notice your exchange at the lungs. So here comes 40 and 45 from the tissue. Then we're going to go ahead and drop off CO2, 5. Okay, and we're going to pick up 60. And notice our numbers, 140. So at the lungs, we're dropping off CO2 and we're picking up O2. Then we go to the next slide. What are we doing here? We're dropping off 55, but we're picking up 5. Now these are pressures, okay, but it's telling you what we're dropping off and picking up. Now, gas pickup and delivery. That's funny. That's like Safeway's grocery delivery, right? That's funny. Okay, but gas pickup and delivery. So blood plasma cannot transport enough O2 or CO2 to meet physiological needs. So RBC cells, red blood cells, okay, transport O2 and CO2 from peripheral tissue, remove O2 and CO2 from plasma, allow gases to diffuse into the blood. So what they're saying is plasma is going to pick up some of it, but your blood, red blood cells, is going to pick up the majority of it. So I know that when we, back in the day, they said, oh yeah, CO2 is all carried in blood. Well, that was kind of a general statement. They weren't just saying red blood cells, they were saying blood, period. Because some of it is carried in plasma and some of it's carried in red blood cells. Actually, the majority of it. Okay? So when you think about this, when someone says it's carried in blood, blood, whole, everything. Plasma and red blood cells. Okay? So when they say that, they mean everything. So oxygen transport, O2 binding to iron ions in hemoglobin molecules. In a reversible reaction, new molecules is called oxyhemoglobin, which we know this already because we actually talked about this in blood. That means it's oxygenated, oxyhemoglobin. So the opposite of that would be what? Deoxyhemoglobin, okay? New molecules called oxyhemoglobin. Each RBC has about 280 million hemoglobin molecules. Each binds 4 oxygen molecules. Wow. That is an insane number. Let's read it one more time. Each RBC, each one, has about 280 million hemoglobin molecules. Each binds 4 oxygen. That's a big number. That's a big number. Okay? Now we really have to think about the unloading and loading of oxygen. All right? Hemoglobin saturation. The percentage of heme units in a hemoglobin molecule that contain bound oxygen. Environmental factors affecting hemoglobin. Well, PO2 of the blood, blood pH, temperature, and metabolic activities within RBCs. Okay? So temperature is going to have an effect on this. Oxygen hemoglobin saturation curve, a graph relating the saturation of hemoglobin to partial pressure of oxygen. Higher PO2 results in greater hemoglobin saturation. Higher partial pressure of oxygen results in greater hemoglobin saturation. Let's say that one more time. Higher PO2 results in greater hemoglobin saturation. Curve rather than a straight line because hemoglobin changes shape each time a molecule of O2 is bound. Each O2 bound makes the next O2 binding easier. Okay? Allows hemoglobin to bind to O2 when O2 levels are low. Okay? So let's see this whole front row. Everybody stand up. Come on. I know it's a tough life. Stand up. Stand up. Okay? Your table and chairs are a hemoglobin molecule. Okay? Let's see what it says. Each O2 bound makes next O2 binding easier. You're all O2. You're going to bind. Well, let's just start off with something simple. You go ahead and sit down. Does everybody see what's happening here? The rest of them are like, oh, I'm not sitting down. One person sat down. I'm not going to sit down. Okay, stand up again. The 4 of you 1, 2, 3, 4. Sit down. Oh! What just happened? Isn't that the coolest test ever? Oh! What just happened? You can go ahead and sit down. That was phenomenal. Did everybody just catch that? If one person sits down, the rest of you are more likely to say, nah. But if you all start sitting down, what happens to the last few? They're going to want to sit down. Like, I don't want to be standing up. Everybody's going to stare at me. Maria's like, I don't care. I'm the lone oxygen that got away. Okay? But that's what they're saying. They're saying each O2 bound makes the next O2 binding easier. And that's a perfect example of it, because before you all sat down, you're like, okay. So the idea is that it makes the binding easier. Okay? And that's the best way to look at it. And I've always done this demonstration, and part of course, the 5th or 6th person always sits down. Always. Because it makes it easier. Now, is blood directly related to our sociological understanding of how we want to sit down if everybody's sitting down? Probably not. But it's pretty interesting how they actually are pretty similar. Okay? So, oxygen reserves O2. O2 diffuses from peripheral capillaries, high PO2, into interstitial fluid, low PO2. Now, we already know this. This is no big deal. The amount of O2 released depends on interstitial PO2. Okay, up to 3/4 may be reserved by RBCs. Okay? Now, it depends on how much. How much do we actually need out there? Now, carbon monoxide, okay, CO2 from burning fuels, this is what I keep getting at, right? Cellular respiration, binds strongly to hemoglobin, takes the place of O2, can result in carbon monoxide poisoning. Okay? Now, hemoglobin or oxygen hemoglobin saturation curve is standardized for the normal blood pH of 7.4. Now, is that an actual true statement right there? What's the number? 7.35 to 7.45. Thank you. Okay. So when pH drops or temperature rises, more oxygen is released. Now that's a test question if I've ever heard it. And I only see like 3 people writing that down right now. So grab your pens and write it down. When pH drops or temperature rises, more oxygen is released. Curve shifts to the right. Okay, so the curve's over here and it goes up a certain way. As pH drops or temperature rises, it shifts because more oxygen is being released. When pH rises or temperature drops, less oxygen is released. The curve shifts to the left. So there you go. Now, the PO2, millimeters of mercury, oxygen hemoglobin saturation percentages, notice the curve. Okay? So hemoglobin and pH, the Bohr effect. So now we have laws. And then we have the Bohr effect. The Haldane's just slightly opposite. Notice I just slightly. The Bohr effect is the result of pH on hemoglobin saturation curve caused by CO2. CO2 diffuses into RBCs. An enzyme called carbonic anhydrase catalyzes the reaction with H2O, which is what? Water. Yeah. Okay, produces carbonic acid, H2CO3. Okay? Dissociates into hydrogen ion and bicarbonate ion, HCO3. So let's I mentioned this. Now you guys actually have to put forth a little bit of effort. I know it's tough because it's hump day. Okay, but here you go. I mentioned at the beginning of this quarter, when we started lecturing and moved out of the nervous system, wow, that was crazy, okay? I mentioned that CO2 and hydrogen go hand in hand. You guys remember me saying that? The CO2 isn't hydrogen, but CO2 and hydrogen go hand in hand. You guys remember me saying that? There it is, right there. The Bohr effect is the result of pH on hemoglobin saturation curve. pH, hydrogen, okay? Caused by CO2, CO2 diffuses into an RBC, An enzyme, okay, catalyzes the reaction with H2O. So H2O, now we have water, then we have CO2, produces H2CO3. Guys, it's basic chemistry. I'm not a chemist and I get this, so work with me here, okay? I personally, me and chemistry don't get along. We don't get along at all, okay? So yeah, but think about it. CO2 and H2O makes H2CO3, okay? Then it says it dissociates into a hydrogen and a bicarbonate. What is bicarbonate? What is a bicarbonate? But keep going. I'm trying to, what's the opposite of acidity? You think? Exactly. That's the beauty of it. Okay? Dissociates into a hydrogen ion and bicarbonate ions. Hydrogen ions diffuse out of RBC, lowering the pH. So guess what? CO2 and pH go hand in hand. They are best of friends. Okay? This example, the Bohr effect, will be on the quiz on Friday. We will also have, it's a quiz. Okay? We will also have the Haldane on there. So make sure you look up Haldane and reference it to Bohr effect. So this is what they were talking about. 7.6, is that basic or acidic? It's basic. Okay? How about 7.2? Well, it's still basic, but it's actually more acidic than we want it to be, right? So that takes us back to the hydrogen, CO2, or oxygen retention. There you go. Okay, whoa. I don't know what just happened there. That was craziness. Hemoglobin and temperature. When temperature increases, hemoglobin releases more oxygen. Temperature decreases, hemoglobin holds on to oxygen tightly. Right? Temperature effects are significant only in active tissue that are generating large amounts of heat. Example, skeletal muscle. Okay? So don't we need more oxygen when you're running? Why? They're hot. It makes sense, but yeah. Weird how that works. Oxyhemoglobin saturation, notice the curve, and temperature. Now I know that they didn't put this in American standards, they left it with European, but that's okay, I'm sure you guys can figure it out. All your computers probably have a translator for this. Okay, so we're, instead of trying to pronounce this wonderful long, okay, phosphoglycerate, BPG, RBCs generate ATP by glycolysis, okay, forming lactic acid and BPG. What is lactic acid? Should we do a test? We could do a test on it in the next 5 minutes. You guys want to do a test of lactic acid? Yeah, remember you guys, remember this? Oh yeah, now you guys are thinking about it. You're like, that was like the most exercise you did all week, huh? You're like, no, I walked. Yeah, that buildup, that burning sensation in there. Why? Because we're not actually sending enough oxygen into that area. So BPG directly affects O2 binding and release. More BPG, more oxygen release. So BPG levels, okay, BPG levels rise when pH increases. pH increases, acidic or basic? Basic, thank you. Good, good, good. Now, when stimulated by certain hormones. Now, if BPG levels are too low, hemoglobin will not release oxygen. Okay, if BPG levels are too low, will not release oxygen. Carbon dioxide transport is generated as a byproduct of aerobic metabolism, cellular respiration. Again, I keep bringing this up, but it's important. All right? CO2 in the bloodstream can be carried three ways. Converted to carbonic acid, which we just saw, bound to hemoglobin with red blood cells, or dissolved in plasma. So literally, let's go back to what I was saying. When they say in blood, that's what they mean. In blood. Not just red blood cells, but in blood, which is plasma also. Okay? Carbonic acid formation, 70% is transported as carbonic acid. All right, 70% H2CO3, which dissociates into hydrogen and bicarbonate. Hydrogen ions bind to hemoglobin. Bicarbonate ions move into the plasma by an exchange mechanism called the chloride shift. Okay, that takes in chloride ions without using ATP. Now, this is, I'm pretty sure we have an image on this. If not, I have some beautiful images of this occurring. The Bohr-Haldane effect and the chloride shift, the movement of CO2 and oxygen into and out of blood. Okay? But if they're not on this, I've got some beautiful ones I'll post for you guys. It really puts it into perspective. CO2 binding to hemoglobin, 23% is bound to amino groups. Okay? Transport in plasma, 7% transported as CO2 dissolved in plasma. So a very small percentage, but still there's some transported in plasma. So there you go. This is actually a good way to look at it because it gives you all your percentages and tells you how it's being transported. So CO2 diffuses into the bloodstream. 7% remains in plasma. 93% diffuses into RBC. 23% binds to hemoglobin. 70% is converted to H2CO3. Okay, if it disassociates, there's our hydrogen, and there's our HCO3, moves out of the RBC into exchange for the chloride shift. My image is much better than this, so I will post those tonight for you guys. Okay? Much better than this. This is okay. No, mine's better. I'll post mine tonight for you guys. Much better than this. This is too cartoony for me. Okay, so we're going to stop on this image. We're pretty close to the end as it is now. But I'll post those. Make sure you pull those up. And I'll also post the exchange so you can write in the numbers. How much is being dropped off? How much pressure is dropping off O2 and CO2 throughout the body? Do you have any questions? I know. It's coming to the end. But like in any race, when you get to the last week, what are you supposed to do? Sprint. Okay? No walking to the finish line. We're going to sprint to the finish line. All right. See you guys tomorrow.